Okay, dear students, today my topic will be relations and its types. Relations and its types. So before starting relations, let me first of all go through some important definitions. The first one is the ordered pairs, or simply ordered pair. What is an ordered pair? If we have a non-empty set A, we have a non-empty set A, and we suppose that you have two elements A comma B in set A. Then if we place the two elements A and B in a particular order or according to a definite arrangement, then the order or the arrangement will be called as the ordered pair. Ordered means a particular arrangement or a definite arrangement. Pair means when we have two elements of a set arranged in some definite order. So ordered pair we can write as A comma B. Here A is called as the first entry and B is called as the second entry. These are also mathematically called as the lattice points. A and B are also called as the lattice points. Then after that, let me give you the best example for the ordered pair. You have the two-dimensional geometry. For example, if we have 2, 3, clearly if we have to plot the point 2, 3 in the xy plane, then clearly we have to go according to certain arrangement. We have to go through the according to certain rule. The rule is, first of all, we have to plot 2. And then accordingly you have to plot 3. So the point will be, total point will be 2, 3. And here we have clearly plotted the point 2, 3 according to a certain definite rule, and hence is called as the ordered pair. Then after that we have equal ordered pairs. Now what are equal ordered pairs? Simply if we have two ordered pairs A comma B and C comma D, then these two ordered pairs are mathematically said to be equal ordered pairs, and we write A comma B equal C comma D if and only if their corresponding entries or their corresponding elements are equal. That is, A equal to C and B equal to D. It means first entry of first ordered pair is equal to the first entry of second ordered pair, and second entry of first ordered pair is equal to the second entry of second ordered pair, and hence the two ordered pairs are said to be equal. The best example for this ordered pair will be if we have 3x comma x plus y equal to 3 comma 4, then clearly the two ordered pairs will be equal if and only if first entry is 3x equal to 3 implies x is equal to 1, and x plus y, second entry of first ordered pair, is equal to second entry of second ordered pair, that is 4. Putting the value of x, that is 1 plus y equal to 4, and hence we can say that the value of y is 3, and the total ordered pair will be clearly, putting the values of x and y here, it will be 3 comma x is 1, y is 3, it will be 3 comma 4 is equal to 3 comma 4, and hence the two ordered pairs are clearly equal ordered pairs. Then we have Cartesian product of sets, or Cartesian product of sets. Simply if we have two non-empty sets A and B, and we suppose you have set A has some element set A and we have B belongs to set B, then clearly the Cartesian product of A and B is denoted by A cross B and is defined mathematically as A comma B, such that A belongs to set A and B is in set B. It means that in A cross B we have nothing but just the set of all those ordered pairs between the elements of set A and the elements of set B. For example, if we have set A equal 1 comma 2 and set B equal 3 comma 4, then clearly A cross B will be equal to 1 comma 3, 1 comma 4, 2 comma 3 and 2 comma 4. So this set of all those ordered pairs between the elements of set A and the elements of set B will be called as the Cartesian product of two sets A and B. Now after that we can clearly conclude a very important result here. In set A we have n of A is 2. N of A means the cardinal number or the cardinality of set A. It means how many elements are in set A. Clearly there are 2 elements in set A and here there are 2 elements in set B. And here we can easily conclude that the number of elements in A cross B is equal to 1, 2, 3, 4. So here n of A cross B is equal to 4. So I can write a result here. N of A cross B is equal to N of A cross N of B. So here N of A cross B we have 4 elements, and so I can write 4 equal N of A we have 2 elements, so I can write 2 cross 2 which is equal 4. So it's a very important result. N of A cross B is N of A into N of B. Now after that let me start a very important topic, that is the relations. Relations. If we have two non-empty sets A and B, then R is said to be a relation from set A to set B if and only if we can write R is subset of A cross B. It means A cross B is the set of all those ordered pairs between the elements of set A and the elements of set B, and clearly R will be again the set of all those ordered pairs. But those ordered pairs should be present in A cross B. Here mathematically we can conclude that in R you have some restricted elements which are already present in A cross B. For example, if we have set A equal 1, 2 and 3, and in set B we have equal 2, 3 and 4, then clearly first of all I will write A cross B. It is 1 comma 2, 1 comma 3, 1 comma 4, then 2 comma 2, 2 comma 3 and 2 comma 4. Similarly, we have 3 comma 2, 3 comma 3 and 3 comma 4. Now here, if we go through some ordered pairs from A cross B, under certain conditions we can write R is defined as x comma y, such that x is less than y, but x belongs to set A and y belongs to set B. So clearly we can write all those ordered pairs from A cross B. It means the ordered pair is x comma y, such that first entry is less than the second entry. So there is important condition on the ordered pair. So I can write all those ordered pairs. Here 1 comma 2 we cannot write because yes, 1 comma 2 we can write here, 1 is less than 2 here. So 1 comma 2 will be having 1 comma 3, 1 comma 4, because all 1 is less than 2, 1 is less than 3, 1 is less than 4. Similarly 2 comma 2 it is not there because we have strict inequality here, less than y. Then we will be having 2 comma 3. So 2 comma 3 we can write 2 comma 4. 3 comma 2 will not be there because first entry is greater than the second entry. Then we will be having 3 comma 4 here. So I will write 3 comma 4. Clearly in A cross B we have exactly 9 ordered pairs, but out of 9 ordered pairs just 1, 2, 3, 4, 5, 6 ordered pairs satisfy the given condition. The condition is x is less than y. So we call this set of all ordered pairs under certain condition as the relation from set A to set B. So what actually is the relation? In relation you have all those ordered pairs but under certain condition, under certain restriction. The restriction will be what the condition you are imposing between the first entry and the second entry. Then you have very important topic, that is types of relations. Types of relations. The first type of relation is the reflexive relation. So what is the reflexive relation? If we have a non-empty set A and we suppose A comma B belongs to set A, then if the relation is defined like this, A is related to A or B is related to B for all A comma B belongs to set A, it means if in set A every element is related to itself, means we can write A comma A belongs to set R, belongs to R, B comma B belongs to R. It means every element of set A, if it is related to itself, then we call the relation as a reflexive relation. The best example for this will be if we have relation R equal to L1 comma L2, means we have two lines such that line first is parallel to line second. In this relation, clearly each and every line is parallel to itself. L1 is parallel to L1, L2 is parallel to L2. So this relation is an example of a reflexive relation. So dear students, what is a reflexive relation? A relation R on a non-empty set A is said to be a reflexive relation if and only if every element of set A is related to itself, or every element of set A have a relation with itself. So we call the relation as the reflexive relation. Then you have second type, that is symmetric relation. So what is a symmetric relation? A relation R on a non-empty set A is said to be a symmetric relation if and only if A comma B belongs to R implies B comma A should also belong to R. It means अगर कोई entry आपके पास है A comma B, it belongs to relation R, then there should definitely be an entry B comma A which will be in the same relation, that is R. For example, we can write here, if A is related to B, then B should also be related to A. So then the relation will be called as the symmetric relation. For example, again let me take the same example. Relation R equals L1 comma L2 such that line 1 is parallel to line 2. Clearly we can write, if we have line L1 here and we have line L2, we can easily conclude line L1 is parallel to L2 and L2 is parallel to L1. So hence the relation is a symmetric relation. So this relation L1 parallel to L2 is reflexive as well as it is symmetric relation. We can have one more example here. Relation R equals, you have two triangles, triangle 1 and triangle 2, such that triangle 1 is similar to triangle 2. Clearly every triangle is related with itself because triangle 1 is similar to triangle 1 and triangle 2 is similar to triangle 2. So the relation will be the reflexive relation. Then after that, if we have triangle 1 similar to triangle 2, it implies triangle 2 is similar to triangle 1. Hence the relation will be the symmetric relation in this case. Then you have the third type, that is a transitive relation. Transitive relation. So what is a transitive relation? A relation R on a non-empty set A is said to be a transitive relation if and only if A comma B belongs to R, comma B comma C belongs to R. It implies A comma C should belong to R. It means if you have an ordered pair A comma B in the relation R and B comma C is in the relation R, then clearly there should be an ordered pair A comma C which will belong to the relation R. Then the relation will be the transitive relation. Or in other case we can say that if A is related to B, B is related to C, then implies A should be related to C for all A comma B comma C belongs to set A. Then in this case the relation will be called as a transitive relation. For example, if we have a relation like this, you have two triangles, triangle 1 comma triangle 2, such that triangle 1 is similar to triangle 2. The relation is clearly a transitive relation. How it is a transitive relation? Because if we take first of all two triangles, triangle 1, triangle 2 belong to R, then we will take triangle 2 comma triangle 3 belongs to relation R. In this case, triangle 1 is similar to triangle 2 because it is given there in the given relation. Then you have triangle 2 is similar to triangle 3. Clearly from first and second we can conclude the result that triangle 1 is similar to triangle 2, triangle 2 is similar to triangle 3. Hence therefore we can write triangle 1 is similar to triangle 3. The relation is a transitive relation here. Clearly we have already gone through this relation earlier. The relation is reflexive, it is symmetric, it is transitive also. So let me take one more example for this transitivity of a relation. We will consider the relation R equal to L1 comma L2 such that line 1 is parallel to line 2. In this case, if you have three lines L1, you have line L2 and you have line L3. Clearly line L1 is parallel to line L2, so I will write L1 parallel L2 and L2 is parallel to L3 because if you consider ordered pair first of all L1 L2, by definition L1 will be parallel to L2. Then after that let me consider L2 L3. L2 will be parallel to L3 and clearly we can conclude from these two L1 will be parallel to L3 and hence the relation is an example of a transitive relation. Let me take one more example. If we have a relation like this R equal to L1 comma L2 such that line 1 is perpendicular to line L2. Let us first of all go through this relation in all the cases, whether it is reflexive, symmetric or it is transitive. Line L1 is perpendicular to line L2. Clearly, line L1 is not perpendicular to line L1 or line L2 is not perpendicular to line L2, but we can say that each and every line is parallel to each other but they are not perpendicular to each other. So we can say that this relation is not a reflexive relation. Then let us take the symmetric part. L1 perpendicular L2, clearly L2 will be perpendicular to L1. So this relation is a symmetric relation. It is a symmetric relation. Then we have the third case, that is transitivity. L1 perpendicular L2 and L2 we will take one more line as L3. L3 is perpendicular to L2. Let me suppose it will be like this. L3 is here. Clearly L1 is perpendicular to L2 and L2 is perpendicular to L3. By the given definition, L1